Hello, everyone. Welcome back. So our first speaker is Namrata Roy from Johns Hopkins University.
Hello. Hello. Is it audible?
Yeah, I think it's
audible. Oh, okay. Can I also hold like a handheld mic? That's easier.
Okay. Use that and
Yeah.
we'll take that off.
Hello. Yeah. All right. Hi, everyone. I am Namrata Roy. I am a postdoc at Johns Hopkins University. I want to first thank the organizers for inviting me here. It's always so nice to come back to Santa Cruz. So I'll be talking about some of the very recent results from a JWST program that I'm involved with. It's about violent feedback from a high redshift radio loud active galactic nuclei. All right, so since I'm interested in AGN feedback, I have to put up a slide about why AGN feedback is important. So everyone here knows, but the energy from feedback is required to explain the massive end of the galaxy luminosity function. Otherwise, we will get galaxies which are too massive, too blue, and too bright. But AGN feedback is important to me personally more for this reason. So the AGN-driven outflows plays a crucial role in the gas cycle in galaxies. So you have AGN-driven winds kind of pushing some gas out. Some of that gas escapes. Some of those gas comes back down, and the gas gets recycled. So that really shapes the star formation rate distribution and morphologies of galaxies as they evolve. And as we have already heard from Garth and Brand's talk in the first session, JWST has been really amazing, and it has given us this amazing data sets only within the first year of its operation. So I'm going to show you briefly some results that we have already seen about quasar-driven outflows and AGN-driven outflows coming out from different groups. So here I am showing 3 different type 1 quasars that have been observed using different programs. And here the different maps show the oxygen O3 emitting gas. And you can see that the different morphologies of this gas. So you see this kind of biconical outflows, you see this spherical distribution, you see these filamentary structures of high velocity gas. So these are all really exciting results. But the main complication here is that the type 1 quasars or unobscured quasars are really bright. So it becomes really an issue to separate out that bright quasar light to see the emission from the host galaxy. So the quasar host galaxy decomposition is really an issue. So in my opinion, in order to study AGN feedback, I think what we should really be looking at is this majestic beasts, this large-scale radio-loud active galactic nuclei, where you see these large-scale jets. Sometimes these jets can extend from several kiloparsecs to megaparsec scale, and you kind of see that these galaxies exhibit feedback in action pretty clearly. And the reason studying these galaxies is more advantageous than type 1 quasars for me is because these galaxies, the central part of majority of these galaxies are obscured. And so that obscuration basically acts as a natural coronagraph. So it blocks off the bright quasar light and helps you to see the host galaxy gas emission much more clearly. So yeah, so the advantages are that the central quasar emission is blocked, and of course, the obvious reason is that we see these jets in action. So these are ideal sites to study feedback and gas outflows. Of course, the radio AGN-driven feedback, the idea of that started in the late 90s, maybe in the early 2000s, where we observed these large-scale radio jets in the cool core clusters. And we saw these cavities created by these radio jets, and people calculated that the amount of energy that is deposited in these cavities is enough to counterbalance the cooling flow in these clusters. But what is not really known until now is how these radio jets interact with the ISM. So in some cases, the radio jets, they drive large-scale outflows. In some cases, it clears the gas out. In some other cases, it compresses the gas, maybe inducing star formation, or in some cases, suppressing it. So there are really like a diverse theoretical work and also observational work that have been done, but we still don't know how radio jets interact with the ISM and how exactly this feedback happens. So what we really need, what we really need, is spatially resolved IFU studies following up this radio loud AGN so that we can map out the gas distribution alongside looking at their radio structures in the various radio surveys. And as I said, some work has been done, especially in the low redshift, using surveys like MANGA and also with instruments like MUSE. So I'm showing some work here. So here I'm showing two different examples. So the top panels show the color composite image of the galaxies with the radio contours overplotted in white. And the bottom panels show the gas velocity dispersion, which is characterizing the motion of the gas. And we actually see that from these works that in some galaxies, in some radio AGN host galaxies, the gas dispersion is pretty high, going up to 1,500 to 2,000 kilometers per second. And in some other galaxies, the dispersion is really low. It's like 200 kilometers per second. So this is really confusing. We don't know exactly what's the breadth of, or what's the range of values that we expect in these sources. And it's even more unknown what happens at higher redshift. So very few resolved studies exist for radio AGN host galaxies at redshift say 1, 2, or beyond. So I'm showing one such work who have looked at redshift 1 to 2 radio AGN host galaxies, and they have mapped their ISM structures. So here you are looking at the radio contours with the colors representing the velocity of the gas, ionized gas. And on the right panel shows the radio contours with the colors indicating the velocity dispersion. And you can see that this is a redshift 2 radio loud AGN, and you can see the velocities and dispersions are extreme. So these are like 1,000, 1,500 kilometers per second. And in fact, in this paper, the authors proposed, then they showed that in general, the high redshift radio AGNs are much more exotic. They have extreme kinematics, they are very gas rich, they have actively star-forming regions exiting 1,000 solar mass per year. So it was very clear that the low redshift radio galaxies and high redshift radio galaxies are not similar. They are very different. So again, at this point, what we really need is to push the redshift space. We need to go higher redshifts, and we need to do these IFU studies of these radio loud AGNs. And that's exactly what JWST will give us. So our program is following up two farthest known radio loud AGNs that we know of. So one is at redshift 4.1, and another is at redshift 5.7. And these also have very interesting Lyman alpha profiles from REST UV. And we are following them up with the near spec IFU. So we are using two different filters so that we cover the entire REST optical to near infrared wavelength range. So we get all the lines that we need. And the total time is around like 24 hours. Of course, the science time is much less. It's like 18 hours. And both the observations for both these galaxies have been done. The second galaxy, we just got data uploaded in MAST, so I haven't really looked at that. But I'm going to talk about this galaxy, the TNJ1338, which is at redshift of 4.1. And yes, we use IFU data, so we get 3D data cubes, so we get spatially resolved spectra for both these galaxies. All right, so this is the galaxy. So you can see the zoomed-in version of this galaxy here. So the background is a color composite image, and overplotted on top in green is the radio contour. So this is an extremely radio loud galaxy. So the radio luminosity is around 10 to the 29 watts per hertz. And just to give an idea, this is extremely high, it's in the high end of the radio luminosity function of AGNs. And the radio continuum is also ultra steep, so it has a spectral index of about minus 1.31, so it's really, really steep. So before going on to the spectroscopic data, let me first show you the images of this galaxy. So we already had HST image for this galaxy, and you can see the image taken in 3 different wavelengths. So this is the first panel, shows the Lyman alpha narrowband image, and you can see this galaxy is really clumpy. It has like 2 distinct regions here. Now let me add the JWST near cam images, and you can see again, so this is the H alpha narrowband image, and you can see this galaxy is really, really bright in emission line. So really bright in H alpha, really bright in Lyman alpha, and of course it's also visible in the other bands. So this clump down there is actually the host galaxy. And this upper region is an extremely line-dominated region. We see that region to light up in ionized gas, but it doesn't have much stellar continuum in that upper clump. But the host galaxy lies down here. So yeah, this galaxy have lots of ionized gas, and the star formation density is also really high. The total star formation rate is about 1,000 solar mass per year. So let me first show you the integrated spectra, and you can see this different types of emission lines that we see. So in addition to O3, H alpha, oxygen 2, there is also H beta in some spaxels, but it falls in the chip gap for some other spaxels. We also see different sorts of emission lines, like we see neon 5, we see neon 3, we see oxygen 1, we see sulfur 3, etc. So these have lots of ionized gas. So let me now show you from the near spec cube narrowband images centered around different emission lines. And this is what we see. So the first panel shows the white light image. So you collapse the cube along the entire wavelength direction. So you get all the light in the first map. The second map shows the continuum image, where you mask off all the emission lines and you get the stellar continuum. And the different panels show the map around different emission lines. So for example, this is the O3 emitting gas, this is O2, this is sulfur 2, this is H alpha plus nitrogen 2, this is H beta, neon 3, oxygen 1, neon 5. And I'll just give you a minute to kind of stare at this beautiful set of narrowband images that we see, and really the various morphologies that we see in these different ionized gas properties. For some ionized gas tracers like oxygen 2 and sulfur 2, you see the nebular line-dominated region to be brighter than the host galaxy. And for some others like oxygen 3 and H alpha, you see the host galaxy to be very bright. We also detect neon 5, as I said. So this is, we only detect that in the host galaxy, so that means that maybe it's coming from the central AGN. So let me kind of dig deep into one of the emission line maps. So what we can do is we can split this O3 map into different velocity channels. So we do that by taking different velocity ranges. So let's say this is the spectra for one of the spaxels. What we do is we collapse the cube along a narrow wavelength region. And here in this map, I'm showing the O3 gas with a lower velocity between 300 plus minus 300 kilometers per second. So basically tracing the systemic velocity of the bulk motion of the gas. And you can see that majority of the low velocity gas lies in this host galaxy. But now if I kind of trace the different velocity channels moving in the higher and higher velocity ranges, you can see that, for example, this is tracing the highest velocity, kind of the wings of the emission lines, which are sometimes associated with outflows. You see that majority of the high velocity gas lie along this line-dominated region, not in the host galaxy, kind of like in a conical way. Now, if I overplot the radio contour for this galaxy, remember this is a radio loud galaxy. So if I overplot the radio contours, so there is radio lobe, which is coincident with this emission line region. So we see really high velocity gas, which is coincident with these radio lobes that we are seeing. So if I show you similar maps for, high velocity along the conical region, coincident with radio lobes. So if I show you similar maps for O2 gas, we see very similar structure. We see low velocity gas all over the galaxy and also in this upper region, but we see high velocity gas only in this line-dominated region in the top. And again, if I overplot the radio, you see these are coincident. This high velocity gas is coincident with these radio lobes that we are seeing. So let me now show you some of the spectra, because spectras, I think, are beautiful. And let me show you the O3 part of the spectra. So this is, again, the map of this high velocity channel of O3 in the left. And let me show you, kind of walk down along this direction. So this is a spectra from the host galaxy. And you can see that, of course, there is a narrow component and a broad component, which is pretty clear. But as you go up along this high velocity emission line dominated region, you see much more weird line profiles. You see really broad, really different components, chaotic kinematics. And yeah, so I feel like this is really kind of extreme outflows that we are seeing here in this galaxy. So I try to quantify that, the width of the line and the velocity offsets as non-parametrically as possible so that I don't contaminate by models, by fitting different models. So I used peak separation, full width half max, and things like W50, which is a measure of the width at a certain, covering the certain percentile of the emission line. And this is what the maps look like. So here again, I'm looking at the spatially resolved map. So this is the map of W50. This is peak separation, and this is full width half max. And you are again seeing these really high values along this linear direction, similar to what we were seeing in this velocity channel. So in this conical region, we are seeing this high velocity gas coincident with the radio lobes. And just to kind of show you the values of the width of the line, so here I'm plotting the full width half max versus the W50 for the O3 and the O2 emitting gas. And you can see that the full width half max exits 2,000 kilometers per second, which is really, really high velocity that we are seeing here. So I have measured some quantities for the theoreticians here, if they are interested. So the total mass of this ionized gas that we are seeing is really huge. It's like 10 to the 10 solar mass. So lots of ionized gas. The mass outflow rate is really large. It's like 300 solar mass per year. But I wanted to draw your attention to these two numbers here. So the jet mechanical energy, which is from the radioluminosity, it's also pretty high, 10 to the 47 arc per second. And this jet mechanical energy is enough to kind of drive this kinetic power of the winds that we calculated from the ionized gas. So really what we are seeing, I think, is this jet-driven outflows, this massive outflows. So here, this is just showing the spatial distribution of mass outflow rate for this galaxy. And you can again see that there are like greater mass outflow rates along this direction because of this obvious dependence on velocity. Finally, I wanted to wrap up by showing our efforts to talk to simulators just to get physical insights of what is happening. So we are talking to a group who are working on hydrosimulations of radio jets. And so what they're doing is they have a radio jet, and which is kind of collapsing against the surrounding multi-phase gas ISM, and they can calculate the temperature distribution, density distribution of gas, and they can also predict the line profiles and the line widths that they see. And we are just in the initial phase of doing that, but even from a first look, we can see that the model predicted lines are very similar looking to our JWST data. So we are seeing similar widths, similar velocity profiles, similar line shapes as what they are predicted. So we are still in the process of doing this, so it's very preliminary. But I wanted to just show you that this is amazing, and we think that there are something here. I'm also interested to hear from simulators here. So if you think that this data interests you, please come talk to me. And I just want to highlight the other projects and topics I'm working on. I just didn't have enough time to show all that. But yeah, I also work on low luminosity radio AGNs, if you have ever heard about red geysers, in the nearby galaxies. I have also worked with Lyman alpha emitters at high redshift and high redshift galaxies in general with JWST. So yeah, if you are interested in any of these, please come talk to me. And I just want to have this key takeaway slide, and I'll take questions.
Questions?
To derive your mass outflow rate, did you have to assume an electron density, or could you measure that
No,
directly?
we could measure that. We have sulfur-2 pretty well resolved, and we see
What was the value, and did it vary spatially?
it did vary spatially a little bit. It was from like 200 to 400, 450 per centimeter cube.
Was it higher closer to the galaxy?
It was higher
Yeah.
closer to the galaxy, yes.
Great, thank you.
There is a question.
We can have a quick question, and our next speaker, please set up.
Hi, I also have a question about